Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Good day, everyone. Today, we will explore the fascinating world of blockchain technologies. We'll dive into key concepts like distributed consensus in closed environment, Paxos RAFT consensus, Byzantine general problem, Byzantine fault-tolerant system. Let's get started. Slide 1. Distributed consensus in closed environment. Welcome, everyone. Today, we'll dive into distributed consensus in a closed environment, a foundational concept in systems without a central authority. Distributed consensus ensures that all nodes in a closed network, where participants are limited and known, agree on a single data value. Why is this important? Because consistency is critical in systems where multiple entities operate without a central controlling entity. Now, let's break this down further. 1. Closed environment. Unlike open networks like public blockchains, closed environments have a limited number of known participants. This makes them more controlled and easier to manage. Point 2. Trust mechanism. Since participants are predefined, the system often relies on rules and mutual trust. This is less complex than trust mechanisms for open networks. 3. Efficiency. With fewer nodes, agreement is reached faster compared to open systems where hundreds or thousands of nodes must agree. Point 4. Scalability limits. These systems work well within their intended scope but are not designed for large, open networks. Think of them as being optimized for quality over quantity. 5. Fault tolerance. They can handle failures, such as a node going offline, without impacting the network's operation. Point 6. Use cases. Examples include financial systems, enterprise-level databases, and permissioned blockchains. Here, data integrity and speed matter more than public accessibility. 7. Security. Restricted access means fewer vulnerabilities, making them inherently more secure. Example: Hyperledger Fabric, a permissioned blockchain, employs this type of consensus. It's used in scenarios like supply chain management, where stakeholders are known. Slide 2. Paxos algorithm. Paxos is a consensus algorithm that ensures nodes in a distributed system agree on a single value, even if some nodes fail. It's essential for ensuring consistency in systems where failures are inevitable but malicious behavior is not expected. Here's a step-by-step explanation of how Paxos works. 1. Propose. A leader node proposes a value to other nodes in the system. Point 2. Prepare and promise. Acceptors, other nodes, respond to ensure that no conflicting values have already been agreed upon. This step prevents inconsistencies. 3. Accept. Once a majority of acceptors agree to the proposed value, it's finalized. Point 4. Commit. The system achieves consensus, and all nodes update their state. Key features. Leader-based. A single leader coordinates the process, which simplifies decision-making. Phases. It operates in two main phases: propose and accept, ensuring reliability. Fault tolerance. Paxos tolerates failures as long as a majority of nodes remain operational. Consistency. It guarantees that all nodes agree on the same value, avoiding conflicts. Applications. It's widely used in distributed databases like Google's Chubby Lock service. While Paxos is reliable, it's also complex to implement, making it more suitable for environments where robustness is a priority. Slide 3. Advantages of Paxos. Paxos offers several advantages that make it a cornerstone of distributed systems. 1. Proven reliability. It ensures consistency even when some nodes fail. Point 2. Fault tolerance. As long as a majority of nodes are operational, the system functions seamlessly. 3. Global acceptance. Paxos is extensively studied and validated, making it a trusted choice for critical systems. Point 4. Deterministic behavior. It avoids conflicts, ensuring only one value is agreed upon. 5. Scalability. While not ideal for very large systems, it works well in small to medium-sized networks. Point 6. Minimal resource use. Paxos doesn't require significant computational resources, making it efficient. 7. Durability. it's designed to maintain consistency even over extended periods. These qualities make Paxos foundational in building reliable systems like distributed databases and cloud infrastructure. Slide 4. RAFT Consensus. Now, let's look at RAFT, a consensus algorithm designed to simplify understanding and implementation. RAFT works by electing a leader to manage log replication among nodes. This leader ensures all nodes stay synchronized. Here's a breakdown of its process. 1. Leader election. Nodes elect a leader responsible for coordinating operations. Point 2. Log replication. The leader ensures that commands added to its log are replicated across all nodes. 3. Consistency check. Followers periodically confirm they have identical logs as the leader. Point 4. Failure recovery. If the leader fails, a new leader is seamlessly elected. Key features. Leader-centric. The leader handles most of the coordination, reducing complexity. Crash recovery. Even if the leader or other nodes fail, RAFT ensures operations continue. Safety. It guarantees no conflicting logs among nodes. Applications. RAFT powers distributed systems like etcd, a key value store used by Kubernetes. Compared to Paxos, RAFT is easier to understand and implement, which has contributed to its widespread adoption. Slide 5. Advantages of RAFT. RAFT's design offers distinct advantages. 1. Ease of understanding. Its simplicity makes it more approachable for developers. Point 2. Leader-centric design. This reduces communication overhead compared to Paxos. 3. Crash recovery. RAFT's seamless recovery ensures system reliability. Point 4. Consistency. Logs remain identical across all nodes, ensuring data integrity. 5. Widespread use. Its adoption in modern distributed systems speaks to its effectiveness. Point 6. Resilient design. It tolerates failures of up to half the nodes -1. 7. Efficiency. RAFT performs well in real-world systems, particularly those requiring high availability. In short, RAFT makes consensus easier to implement without sacrificing reliability. Slide 6. Byzantine General Problem. This slide focuses on the Byzantine general problem, a key challenge in distributed systems. Let's begin by understanding what this problem represents. Imagine a group of generals planning a coordinated attack on a city. They must agree on a single plan, attack or retreat. However, some generals could be traitors, sending conflicting or false messages to disrupt the decision-making. Despite this malicious behavior, the loyal generals must reach a consensus to execute a unified strategy. This is the essence of the Byzantine general problem in distributed systems. Now, let's break it down further. 1. Message exchange. Each node, or general, shares their decision proposal with all other nodes. This ensures that every node has visibility into the proposed actions. 2. Majority agreement. Nodes compare the received messages to identify inconsistencies. Honest nodes will follow the majority, discarding any contradictory information. 3. Consensus. When enough honest nodes agree on a single decision, consensus is achieved. 4. Fault tolerance. This system can tolerate failures as long as fewer than 1/3 of the nodes are dishonest. A practical example is blockchain networks. In these systems, participants, miners or validators, need to agree on the validity of transactions, even if some nodes act maliciously. Understanding this problem is crucial because it forms the foundation for secure and reliable distributed systems where trust cannot be assumed. Slide 7. Byzantine Fault-Tolerant (BFT) Systems. Building upon the Byzantine general problem, the slide focuses on Byzantine Fault-Tolerant (BFT) systems. What are BFT systems? These are systems designed to operate correctly even when some nodes act maliciously or fail entirely. Let's explore the key features. 1. Fault tolerance. BFT systems can handle both benign and malicious faults. This makes them extremely robust in environments where trust is uncertain. 2. Quorum-based decisions. Consensus in BFT systems requires agreement from a specific subset or quorum of nodes, ensuring that no single malicious node can disrupt the process. 3. Efficiency challenges. Achieving consensus in a BFT system requires significant communication among nodes, which can slow down the process. 4. Deterministic consensus. BFT systems are designed to produce a single, reliable outcome, even in the presence of adversarial behavior. 5. Applications. These systems are widely used in high-security environments, such as blockchains and critical infrastructure systems. Examples include Hyperledger Fabric and PBFT, Practical Byzantine Fault Tolerance. To summarize, BFT systems are critical for applications requiring high levels of trust and security. However, their implementation comes with trade-offs in terms of scalability and resource usage. Slide 8. Advantages of BFT systems. This slide highlights the strengths of Byzantine fault-tolerant systems, making them essential for secure distributed environments. 1. Robust security. BFT systems are resilient to malicious behavior, ensuring reliable operations even under attack. 2. Fault tolerance. These systems can handle both accidental failures and deliberate sabotage. 3. Cryptographic safeguards. Advanced encryption techniques protect communication and ensure data authenticity. 4. Consensus reliability. By design, BFT systems guarantee consistent and reliable outcomes. 5. Critical applications. BFT systems are vital for applications requiring stringent trust guarantees, such as financial networks and blockchain platforms. 6. Redundancy. Data is replicated across multiple nodes, ensuring safety even if some nodes fail. 7. Blockchain relevance. BFT is foundational for maintaining trust and decentralization in blockchain systems. These features make BFT systems indispensable for secure and fault-tolerant distributed applications, especially in environments where participants cannot always be trusted. Slide 9. Challenges of BFT systems. While BFT systems are powerful, they come with their share of challenges. Let's go over the key points. 1. Communication overhead. Achieving consensus involves extensive message exchange among nodes, leading to latency and inefficiency. 2. High complexity. The algorithms required for Byzantine fault tolerance are intricate, making them difficult to design and implement correctly. 3. Scalability issues. BFT systems are best suited for smaller networks, as performance degrades significantly with an increasing number of nodes. 4. Resource demands. These systems consume considerable computational and storage resources due to their redundancy and communication requirements. 5. Implementation difficulty. Developing and debugging a BFT system requires a high level of expertise and effort. 6. Quorum dependency. BFT relies on quorum agreements, which can become a bottleneck or a point of failure if not managed carefully. 7. Cost. Maintaining the redundant infrastructure necessary for BFT systems can be expensive. For instance, scaling BFT for large blockchain networks, like Ethereum, remains an ongoing challenge due to these limitations. Slide 10. Insights on distributed consensus. This final slide wraps up the key takeaways on distributed consensus. Let's discuss the insights. 1. Closed environments. Consensus mechanisms are simpler in permissioned networks with limited participants. 2. Paxos and RAFT. These algorithms highlight the balance between robustness and simplicity in achieving consensus. 3. Byzantine fault tolerance. BFT systems address the challenge of malicious nodes, making them vital for trustless environments. 4. Scalability challenges. As distributed systems grow, optimizing consensus mechanisms becomes a critical focus. 5. Hybrid models. Combining different consensus mechanisms can address specific limitations, improving overall efficiency and security. 6. Real-world relevance. Distributed consensus forms the backbone of systems like blockchains, cloud computing, and distributed databases. 7. Future directions. Research continues to explore ways to reduce complexity, enhance scalability, and improve security in consensus algorithms. Understanding these concepts equips you with the knowledge to design robust and scalable distributed systems, a skill increasingly valuable in modern computing environments.